Great.
Mute myself. Thank you for coming to my talk. You can hear me, yeah?
Yeah, looks good.
Okay. Yeah. So today I'm going to be telling you about spectroscopic diagnostics of fracton phases. So just to set the scene, I mean, there's been lots of beautiful theory work done on fractons, much of it which we've heard about in this conference. But at the end of the day, we're physicists and not mathematicians. So we'd like to actually be able to connect to experiment. And the dream in that regard would be a laboratory realization of fractons in some solid state system, let's say some frustrated magnet. Yeah. But suppose some oracle told you that here's a material, some lump of stuff, and it realizes a fracton phase somewhere in its phase diagram. How would you actually verify if this was correct? So we have lots of nice theorist diagnostics, topological degeneracy, entanglement entropy, Friedenhagen-Marcoux order parameters, but none of these are things that we could go to an experimentalist and ask to measure. Yeah. So what we would really like is experimentally accessible diagnostics. We would like things that can be measured using currently available experimental technology, which nonetheless yield unambiguous signatures of fractons. So that's what this talk is going to be all about. I'll remind you, we can divide fractons up into gapless and gapped, and also type 1 and type 2. And I'll discuss various scenarios. So I'll start by telling you about how to detect gapless type 1 fractons. And the diagnostic par excellence there will be neutron scattering. So you do neutron scattering on a system if you think it has gapless type 1 fractons. And if it does have them, then you should see pinch points in neutron scattering. And those pinch points should be multifold pinch points. They should have higher symmetry than for conventional spin liquids. Then I'll talk about gapless type 2 fractons. So gapless type 2 fractons, again, you can see in neutron scattering. And here the pinch points have a characteristic needle-like structure where the contours are nonlinear. And it turns out that gapless type 2 fractons also have characteristic signatures in the heat capacity. So that's forthcoming work. And then I'll move from gapless systems to gap systems, and I'll talk about how you could diagnose gapped fractons. And gap type 1 fractons will turn out to have characteristic signatures in both linear and nonlinear response. And as a bonus, the diagnostics and nonlinear response will also turn out to work as diagnostics for gapped conventional spin liquids like the Z2 spin liquid, and thereby will also sort of solve a long-standing problem of how do you actually detect a gapped conventional spin liquid. Okay, so let's get down to it. We'll start with gapless systems. So let's start by discussing a gapless spin liquid. Now, this could either be a classical spin liquid like spin ice or a quantum spin liquid. And the assumption is that if you have a gapless spin liquid, then you have gapless emergent gauge fields. And the Hamiltonian might look something like this. Can you see my cursor? Yeah. The Hamiltonian might look something like this, sort of Maxwell type Hamiltonian, where I want to emphasize that E and B are just the emergent gauge fields, they're not the microscopic electric and magnetic field. And there might be a Gauss law constraint that looks something like this. This is just conventional vector spin liquids. Yeah? And the way to see this is to do a neutron scattering experiment. So if you do neutron scattering, well, what you're actually measuring is some spin-spin correlation function, but spin-spin correlation functions are given by superpositions over correlation functions of these emergent electric fields. And correlation functions of these emergent electric fields look something like this. So this expression is for classical spin ice. If we were dealing with a quantum spin liquid, then this constant 1/k prefactor would get replaced by omega of q. But the point is that there's this complicated tensor structure, which comes from Gauss's law. And this tensor structure produces these characteristic pinch points with twofold symmetry, which are a nice diagnostic for conventional spin liquids, whether classical or quantum. Okay, so now let's move on to gapless type 1 fracton phases. So these are believed to be described by symmetric tensor gauge theories. That's what Mike Pretko pointed out 5 years ago. So the Hamiltonian looks very similar. It's a Maxwell type Hamiltonian, but now written in terms of these rank 2 symmetric tensors. You have a more complicated Gauss law, a more complicated gauge transformation. What I've written down here is the scalar charge theory. There's other theories, vector charge, traceless scalar charge, and we worked all of them out in this paper. I'm just going to present the results for one of them. All of them look sort of morally similar. So you go ahead and you examine it in neutron scattering. What you're measuring in neutron scattering is a spin-spin correlation function, but that's related to the correlation functions of the emergent gauge fields by some structure factor, which depends on microscopics. And this correlation function for the gauge field has this complex tensor structure, more complicated than before, but importantly, it has this pinch point singularity, and the microscopic spin-spin correlation function should inherit that singularity from this correlation function of emergent electric fields. And this time, the singularity has an emergent fourfold rotation symmetry. Yeah, so that's the key distinction. So if you have a conventional vector spin liquid, you would expect neutron scattering to see pinch points with twofold rotation symmetry, whereas for type 1 fracton phases, gapless type 1 fracton phases, you would expect to see pinch points with multifold rotation symmetry. So in this case, it's fourfold. No, it could also be a sixfold or eightfold or something more, but you should see pinch points with enhanced rotation symmetry. And this is neutron scattering is a standard experiment. You can do it. And this is a clean diagnostic for a gapless type 1 phase. Let's move on from type 1 to type 2. So type 1 phases, symmetric tensor gauge theories. For type 2 phases, we'll use the formalism of multipolar gauge theories introduced by Gromov. So the idea here is you start by defining some derivatives, which could involve like mixed rank derivatives, so some first derivatives and some second derivatives. These then define for you some polynomials, which are annihilated by these derivatives. And those polynomials define certain combinations of multiple moment which are conserved. You have a sort of generalized gauge transformation, generalized electric field, generalized Gauss law, generalized magnetic field. And now you can go ahead and you can write down a Lagrangian. So here, epsilon and G are arbitrary, positive definite symmetric matrices, but other than that, they could be whatever. And here's the generalized Maxwell type Lagrangian for a gapless type 2 phase. And what I'm going to say is essentially going to be generic for gapless type 2 phases of this sort. To do the actual calculations, you need a particular theory. So we'll use the, so we'll specialize to the U1-Ha code, and specifically Gromov's treatment of the U1-Ha code. But the key properties are going to be general, and I'll sort of highlight what I think the key properties will be. So for the U1-Ha code, these three are the emergent derivatives. L2 and L3 are ultraviolet length scales, so we can just set them equal to some lattice scale A. And there's a nonlinear relationship between these derivatives. We can define the fields, E1, E2, E3 as before, B1, B2, B3. And we can also define an additional magnetic field, B4, in this way, which is not linearly independent to B1, B2, B3, but it's another term you can add to the Lagrangian. And I will consider the most general Lagrangian you can write down, which looks something like the following. And now you can go ahead and you can find the equations of motion. You solve the equations of motion, and you see that there's exactly one gapless photon branch, and that gapless photon has the dispersion relation that's shown on the bottom line of this slide. So here we're working on the cubic lattice, and QU is the momentum in the 111 direction. Q rho is the momentum orthogonal to 111, and A is the lattice constant. Yeah. So we have one gapless branch. If we're working at temperatures much below the charge gap, our signal will be completely dominated by this one gapless branch. So now we go ahead and we compute correlators for neutron scattering. So we could compute some correlator like E alpha, E beta. This is what we're going to see in neutron scattering. I'll emphasize that alpha and beta here are not Cartesian indices. They correspond to these invariant derivatives in the multiple gauge theory formalism. And here the X's are the polarization vectors of this gapless photon. And this is the inner product in the denominator. And you work out this correlator, and you find that now the scaling with momentum depends on which direction you approach in. So now you get a pinch point, but it's this needle-like pinch point where the contours, instead of being linear, as in the type 1 case, instead you have these parabolic type contours. And that's ultimately coming about because the Gauss law for a type 2 theory has mixed derivatives in it. It has some first derivatives and some second derivatives. And that, and it's this Gauss law that produces the tensor structure and the pinch points. And because the Gauss law has mixed derivatives, the contours for the pinch points are nonlinear. Yeah, and so we expect this feature to be completely generic for any type 2 theory with mixed derivative Gauss law. So this is how we can just differentiate conventional vector spin liquids, type 1 fractons and type 2 fractons. Vector spin liquids should have linear contours and twofold symmetry. Type 1 fractons should have multifold pinch points, but still linear contours. And type 2 fractons should have arbitrary polynomial contours. So in this case, it was parabolic. You could imagine cubic or quartic or something instead, but sort of not linear. And all of these can be seen in neutron scattering. So you just go to your neutron scattering experimentalist friend and ask them to do neutron scattering and look for pinch points. Yeah. So this was for gapless. Oh, one more thing I should mention. For the type 2 fractons, you can also see things in specific heat. So the Gauss law has mixed derivatives. The dispersion relation has mixed derivatives. You go ahead and you compute the specific heat capacity, and you find that in 3 space dimensions, the heat capacity scales as T squared, where T is temperature. So this is sort of unique. I don't know if any way to get this, at least in some free quasi-particle theory. If you had something very exotic, then like quantum critical point with variable exponents, then I guess you could get whatever. But in any case, if you worked with some 3D material and you saw T squared heat capacity, then that's a strong signal of exoticness. And type 2 fractons is one way to get it. And then you could go look for pinch points to confirm. Okay, so far we had talked about gapless systems. Now let's move to talking about gap systems. So gap systems are much harder to diagnose. And that's even true for conventional spin liquids. So if you have a toricode phase, how the hell do you actually diagnose it? And the problem is that if you have a spin liquid or a fracton system, then elementary excitations are created at the ends of non-local operators. They could be either string operators or membrane operators, which means that local probes create multiplets of excitations. So if you've got a string operator, then you can create 2 spin-ons, momentum plus minus k, and you can create them with 0 net momentum at a variety of different energies. So in absorption, you just see a broad continuum. And this makes it hard to cleanly identify the phases spectroscopically. Yeah? It makes it very hard to identify conventional spin liquids spectroscopically. For type 1 fractons, things are a little better. Because if you have a type 1 fracton phase with line-on excitations, then in fact there is a sharp signature, because the line-ons will give rise to a one-dimensional Van Hove singularity in the absorption spectrum. And so if you have a bulk material and you observe one-dimensional Van Hove singularities in the absorption spectrum, then that's a sort of strong suggestive signature of line-ons in the problem. Yeah. But what if you weren't lucky and you didn't see one Van Hove singularities, or what if you didn't have line-ons, right? So in that case, what you need to do to get sharp signatures is you need to look at the nonlinear response. And in particular, what you want to do is you want to use the technique of 2-dimensional coherent spectroscopy, abbreviated 2DCS, which turns out to provide unambiguous diagnostics of gap type 1 phases. And also as a bonus, it provides unambiguous diagnostics of conventional gap spin liquids. So what is the 2DCS experiment? The idea here is that you shine 2 pulses in the system. Typically, you want them to be in the terahertz regime to match sort of spin energy scales. Their 2 pulses can be called A and B, and they're shone on the system at times 0 and tau. And then you measure the response of the system at a time tau plus t. And what you want is the nonlinear response. So you get the nonlinear response by taking the response in the presence of both pulses, A and B, and subtracting off the response with only pulse A and the response with only pulse B. And this gives the intrinsically nonlinear response. Yeah? So now let's connect theory. You can go ahead and you can calculate the nonlinear susceptibility in some generalized Kubo formula. And you can do this for the perturbed toric code, perturbed X cube, like whichever model you want to work with. And you get some complicated expressions, which I don't want to go into right now, the S factors and matrix elements. But the key point is, how do you analyze this? And the way to analyze this is that this response function depends on 2 times. There's tau, the time delay between the 2 pulses, and there's t, the time interval between the second pulse and the measurement. And you Fourier transform with respect to both, and then you plot the result in the 2-dimensional omega tau omega t plane, and you see what you get. Yeah. And so to skip the details, what you find is that now in the 2-dimensional plane, you have distinctive signatures for each of the following: deconfined quasiparticles, whether those deconfined quasiparticles can further fractionalize, and whether any of the elementary excitations are immobile, i.e. fractons. Yeah? So this means that this 2DCS experiment is a good diagnostic for gap spin liquids and also for gap type 1 fracton phases. Now, I want to clarify, 2DCS can tell you if you have a gapped spin liquid phase. It cannot tell you if you have toric code or double semyon or something else. Yeah? Similarly, it can tell you that you have a gapped type 1 fracton phase, but it can't tell you if you have X cube or checkerboard or something else. Yeah? So it can tell you sort of whether you're dealing with a gap spin liquid phase or whether you're dealing with a gapped type 1 fracton phase. It cannot tell you which one of them you're dealing with, but that's still a good start, because I don't even know of any other experiment that can tell you if you do have a gapped spin liquid phase or if you do have a gapped type 1 fracton phase. I want to emphasize that this work is not limited to the solvable point. So a lot of works on 2D CS are solvable points. Our results are expected to be valid throughout the phase, but it is limited to a frequency window that's above the gap but below the multiparticle continuum. So if we were working with the toric code, then we're working at a frequency where you can make 2 spin-ons but not 4. Okay. So to conclude, so gapless type 1 phases can be diagnosed via these higher multifold pinch points. Gapless type 2 phases can be diagnosed via pinch points and neutron scattering with nonlinear contours. Gapless type 2 phases can also be diagnosed via heat capacity. Gapped type 1 phases with line-ons can be diagnosed through Van Hove singularities in linear response. And gapped type 1 phases without line-ons and also gapped conventional spin liquids can be diagnosed through the nonlinear response using the technique of 2DCS. The only thing remaining is how do you diagnose gap type 2 phases? Now, in principle, you could do this with some very high order nonlinear response, but that's not really a realistic experiment. I don't have a good idea at the moment for how to diagnose gap type 2 phases in a realistic experiment, so that problem is still open. And of course, there's the question of, well, okay, now we know what to look for, but where should we look? What's a good candidate material? So with that, I'll just thank the various collaborators with whom I did these various works, and I will conclude.